All right. Hi, everybody. I'm Chris Jensen.
I am Brian Words.
And I'm Shan Chapter.
So yeah, we're making a handheld oscilloscope. Just a brief overview of what we're going to cover, the aims of the project, our specifications, an overview of our system, where we are with all the subsystems. There's a demonstration at the end, and then we'll have a brief conclusion and hopefully time for questions. So the aims of our project was to create a compact oscilloscope that offers all of the basic operations of a typical lab scope, and that's a significantly reduced cost. And here are some pictures. They're a little small, but we have bigger ones later that go into more detail.
So here are the basic specifications of our oscilloscope. As Chris mentioned, we want it to meet that of a typical lab scope. So that includes an input, an analog input bandwidth of 20 megahertz, peak input voltage, 0.1 to 10 volts with an ADC sampling rate of 50 megahertz. We can also decimate that ADC sampling rate inside of the FPGA from 1 to 1 all the way down to 50 to 1. We're using an input of a BNC connector with a 1 mega ohm impedance, which is typical of an oscilloscope, as well as in terms of functionality, threshold, rising, falling edge, auto, normal, and single triggering modes. We also have a SPI data transfer rate for the communication between two of our subsystems at 10 megabits per second, an ADC precision of the sampling of the analog input data at 10 bits. The FPGA buffer size, which is how many data points we can hold, is 512,000 data points at 8 bits per sample, and a display resolution of our oscilloscope, 320 by 480. This diagram shows the overall system, as well as in blue, the flow of data between these three subsystems that we have. Beginning on the left is the data acquisition board. This was completed, this is being done by Shannon. It involves the BNC connector, signal conditioning, and the analog to digital converter, which sends the data to the FPGA. The FPGA handles the data storage and logical operations, and this was done by me. And lastly, to the right is the microcontroller unit, the MCU, which handles the data display and the control interface between itself and the FPGA via a SPI interface. You'll hear us using terms like SPI master and SPI slave. Those are the industry standard terms for a SPI interface. There's currently a movement in the EC industry to adopt better and more sensitive terminology, but we're going to continue using the standard terminology for the purpose of this presentation. As well, you'll also probably hear us say DAB, that's the data acquisition board. As I said, MCU is the microcontroller unit, and FPGA is the FPGA.
So here we have the subsystems of the data acquisition board. As Brian had mentioned previously, we have the analog to digital converter, which converts the analog signal to binary numerical values. We have the variable gain amplifier, where the gain is set via the MCU DAC, and the signal conditioning, which provides a DC offset to match the ADC input value range, and a low pass filter that controls aliasing.
For the FPGA subsystem, the field programmable gate array, we're using the Nexus Arctic 7 FPGA, which was kindly provided to us by the College of New Jersey to use for this project, as well as all programming simulation being done using Verilog inside of the Xilinx's Vivado Design Suite program. The FPGA is the central module of the whole system. The data is entered here from the ADC on the DAB. It's stored, operated on, sent to the MCU. Beginning with these first two subsystems of the FPGA, we have the VGA out, video graphics array, that's used to output an analog signal to the data acquisition board. There's no actual video graphics going on. It's just being used purely for an analog signal. And the timing generation the timing generation module, this creates the ADC sample clock. We also have the ADC interface, which handles the data input and the bit selection to allow us to go from the 10-bit input from the ADC to the 8 bits that's being used inside of the FPGA and into the MCU, as well as the RAM, which stores the data. We have the RAM write engine and trigger logic modules. The RAM write engine that handles the addressing and enabling for writing to the RAM, and the trigger module, which is a pretty complicated module that involves all of the trigger logic used in the FPGA. Continuing on, the RAM read engine module and the FIFO module. The RAM read engine handles addressing when reading data, much like the RAM write engine does for writing. And the FIFO controls the data flow between the RAM and the SPI slave module. The SPI slave is where all the interfacing between the FPGA and the MCU is done. And the registers is a very important module in the FPGA. This handles all of the control values, as well as some basic read and write operations between itself and the MCU to allow for us to control what's going on.
And this is for the MCU/the display. So the MCU itself communicates with the FPGA board and the data acquisition board, and it will send configuration, receive data samples, and displays a trace based on user set parameters. The display itself is an LCD panel with RGB color display, has a touch screen, and there are multiple settings that the user can control that impacts the display. You'll see another picture on the next slide. And we used a little VGL, which is a free graphics library and lightweight real-time operating system. And that's used for all of the interactive components, the widgets, and a lot of the display features. Here's a breakdown of the board. The red box is the touchscreen and the display. The blue is the PCB board, and the yellow is the PSOC module. And the board itself was actually developed for a separate research opportunity at TCNJ by Jordan Jacinoway, who I think had a presentation earlier in the day. So we just expanded on it.
Okay, so as for the DAB design, the components were chosen based on the developed requirements and system specs that we had mentioned earlier. And we needed to verify this through simulation before the construction could begin, which I had done in Eagle. And right now we are working on the bring up and testing of the DAB. This includes continuity and short check between the power and ground, voltage regulator and terminal block, which I will point out later. We are testing the functionality of that, as well as the VGA amplifier and ADC within the DAB PCB. This is the architecture for the DAB. There is a BNC connector that connects to the variable gain amplifier, where an analog gain control voltage is received from the MCU, which then passes over to the amplifier for signal conditioning, where a offset is obtained from the FPGA, and there is a low pass filter in there, as well as it moves on to the ADC, the analog to digital converter, which interfaces with the FPGA with the PMOD connectors. This is the Eagle schematic that I had created for the first version. This is currently being looked at, reviewed. There was a couple mistakes that we had noticed, some hiccups that we are working to fix by the end of the semester, which was partially implemented in the physical board, which you will see in upcoming slides. This is the board that was generated from the Eagle schematic. This is what we had sent out to get produced that we could then build the DAB on. So this is a picture of the current DAB hardware. Couple things to notice: there are a couple resistors missing, things that need to be jumpered across, some connections that need to be fixed. But other than that, we are still doing testing to find any other issues that we may have. And this is just a picture of the back of the board in case anybody was curious.
So this is just an overview of the register module that I mentioned earlier inside of the FPGA. The first 6 registers, 0 through 5, those are used for debugging, not included here. No reason to go over each and every one of these, but important ones of note would be the on bit that's controlled by the MCU, determines when we're sampling, when we're not sampling, as well as the triggered register, register 15. This is a register that's constantly read by the MCU and allows the MCU to communicate with the spy master. Since there's no way for the spy slave to send a command to the spy master, we have to go through other means like this, such as these constantly reading registers.
So here's the SPI interface we're using. On the top, you can see there's the SPI select with active low, SPI enable. And then there's the clock, and we sample on the positive edge. Then there's MOSI and MISO. And then actually when the data bits come from the slave. We have 3 commands: read register, write register, and read RAM. And those are denoted in the first 3 bits of our command word. So that's on the bottom. You see CMD is the command on the bottom left of that, and then there's the parameters where I'll say like what register we're writing to, and then the actual data that's being transmitted. That's a total of 16 bits, the word. Here's just a flow diagram of the MCU software. The blocks in blue is what is automatically generated by PSOC, and pink is code that we worked on and wrote. I won't go too much into it, but basically there's an infinite loop that constantly checks if the user is interacting with it. And based on that interaction, it will set parameters that are told to Brian's FPGA board and the DAB. So here's the MCU currently. There's a picture of it. You can scroll horizontally, there's offset, and all these other parameters that you can see. I don't want to go too in depth because the video shows it better. But you can, all of those are adjustable. And the trigger still needs to be implemented, and some more SPI commands, but it's it's looking good right now. So currently the MCU and the FPGA submodule are integrated together. The sending and receiving of commands and data is operating as expected via the SPI interface. But the DAB and the FPGA are nearing integration. As Shannon mentioned, we're still testing that. So once that's in a good spot, we'll be able to integrate those as well. So I guess I'll just talk over this. You can see that there you're able to move across the amount of data points you have read in. There's the offset that will vertically adjust where the signal is being read. You can change the horizontal scaling. We have 100 millivolts, 200 millivolts, 500 millivolts, 1 volt, and 2 volts, which is the same amount of options you have for the vertical scale, which is now being shown. You can see it being adjusted. Offset again. Then there are just some other things that you can say. Probably could use some text, but it's using auto threshold. You can change your trigger settings. As I mentioned earlier, trigger still needs to be implemented fully, but you're able to change it how you wish, and that will eventually be written to Brian. There's an on and off, and that's just the functionality that's there. So mostly implemented, but still some work to do. Oops, sorry.
So here, if anybody's interested in some more information, we have our website, a link to our website. I don't know if these slides will be available. I suppose you could either get it from the TCNJ website or screenshot and type this in later. But here we have all of our, on this site, we have all of our old presentations, such as our semester 1 report, as well as the actual documents being used, such as various diagrams we're using, and the actual presentation slides are on here as well.
And then just a quick summary, we're working towards an oscilloscope that will have mainstream features and perform that in the level of that of a lab oscilloscope. And we estimate the cost of goods sold to be about $50 for a commercial version of our design.
Okay, I see one question from Lou Samsel. When your project is completed, who do you see as your target market to purchase it, and how do you foresee they will use it? So when we began this project last spring, I think the greatest inspiration for us was the really sudden shift to fully remote learning. As a result of that fully remote learning, a lot of students, especially young engineers, are not getting the necessary technical knowledge that you would be getting if you were going in person to a lab. Specifically, a really, really important skill is the use of an oscilloscope. So widely, we don't think we'll ever be able to compete with like the Amazon Basics introductory oscilloscope, but we still think it'll be a really great educational tool for use for mainly students, engineering students, widely distributing it for them.
Yeah, I think Brian hit the nail on the head on that one. But yeah, the ability for schools to send this out to students, whether it just be to learn an oscilloscope or just other labs, because right now a lot of labs are forced to be software only. Having an oscilloscope, a small one like this, would really expand the possibilities of what students can learn. That'd be really useful for the underclassmen, like sophomores and freshmen, just because they haven't had the experience in the labs yet.
I'll read out the next question. If anyone else wants to answer, they can first. Being critical of your design and what you've observed, what, if any, are the key differences, maybe limitations of your implementation compared to the more expensive lab scope? Related to that are uses that you recommend for your design and use cases that you don't recommend for our design.
I can start with that. Just at least for the MCU itself, this is a board that we took from a research project, so it's not specifically made for this. So there's definitely room to improve the MCU itself. It could use a bigger screen just because it's very limited on how much you can see, as well as the memory inside it. So that's definitely a limitation. And if like I was to do an iteration 2, we would make our own board for that. And if anyone else have anything they want to add about their own.
I was also thinking that one of the big things is we're only displaying 8 bits worth of data. A really expensive lab scope is going to be using a lot more than that, having significantly more detailed data. I think that's a very a big one as well, as the number of the size of the data we're using and able to use.
I don't think I have anything to add to that. That was, you guys about covered what I was thinking, at least.
Okay, I think we're out of time. I'll read Brock's thing real quick. Good breakdown. I like the approach trying to solve the problem of financial accessibility and general availability of devices like this for a wide variety of users. I really enjoyed the presentation, learned a few things. Thank you, Brock.
Yes, thank you.
Yes, thank you.